Hello everybody, today I will present to you my static system solver. If you have had a mechanic physics class before, you will probably have done some problems like this. They are easy problems, but can sometimes be long and repetitive. That is why we are going to automate that. First of all, let's start by solving a problem by hand. Here we have a beam, with a wheel, a hinge, and a force. We want to determine what are the forces at the wheel and the hinge. Step 1 is to draw the free body diagram, representing the wheel and hinge constraints as forces. The wheel only blocks movement in one axis. The hinge blocks movement in two axes. We have three equations at our disposal for finding three unknown variables. How convenient! Since this is a static system, we want the sum of forces and moments to be zero. Finally, we get our results, which intuitively make sense. The wheel is pushing against the wall, and the hinge resists being pulled upwards. Now we will do the same problem with the program. Let's run the program to see the results, and then I will explain how it works. The program solves it like a system of linear equations. It prints the matrix before solving, and after solving it. As you can see, we got the same answer. Okay. We create a new instance of the system class. We now define all the points in the system, even those which don't have unknown variables. Then we define the parts. In this example there is only one part. Now the constraints and the forces. Finally, we can create a system of linear equations from this information, and solve it by Gaussian elimination. The system class is messy, but it does the job, for now. So the first method creates a new point. Every point has a position. It can also have forces, a moment, and a constraint. The moment is just a number, because in 2D there is only one axis of rotation. The methods getKnownVars and getUnknownVars is for getting a list of all the variables, so that we can easily make rows for the matrix. The function updateMatrix gets every equation as a line in the matrix. You get the coefficients of the variables, and then the sum of the forces/moments. Each part adds 3 equations, and each intersection adds 2 equations. A good old Gaussian elimination. It will probably need optimization for more complex systems. Let's do another example. This time, there are multiple beams and intersections. If you were doing the problem by hand, this is how you would draw the free body diagram. However, the program does not do it like this. Actually, the force at the point B is not the same in the part ABC and the part BD, same goes for the other intersections. Since there are only 2 parts at intersection B, we know that Bx is the opposite of B'X, thus we can reduce the amount of variables, but the program does not know that. Also, if there are more than 2 parts at an intersection, we have to consider the forces separately anyways. This is the code. Okay, the results matrix is quite big, so let's make it a bit more organized. Nice, and it does it so quickly too. Let's do a final example. This time we have a little truss bridge. Some intersections have more than 2 parts, and there is also a torque of 1 kN/meter. Getting the force at every point would be very tedious, even more if we want to plot the change in forces depending on the load. Here is the bridge represented in the program. We will loop, and increase the moment by a bit every time. Also, we shall analyze the forces at point C. As you can see in the code, we update known vars every loop, but we don't need to update the unknown vars, and in doing so, save like 5 milliseconds. It's satisfying to see how the forces at point C change. You might have noticed how the number of known variables is a bit off. It is supposed to be 2, but the known variables are repeated multiple times if they are at an intersection. So that's about it for this video. I guess you could call this the devlog number 1, since I'll most likely make more videos about this. I have plans for making a 3D version, and adding calculations for internal stress. Thank you for watching.